Hello everyone, in this video I'm going to show to you how to evaluate this integral of e raised to negative x squared dx from negative infinity to positive infinity. This integral is called the Gaussian integral, or sometimes known as the Euler-Poisson integral. To evaluate this, let me draw the graph of e raised to negative x squared, which we will be using for our evaluation. E raised to negative x squared can be rewritten as 1 over e raised to x squared. Now let me draw the axis first. The x-axis here is x, and the y-axis here is the value of this expression. When x is 0, the denominator of our expression will be 1 because e raised to 0 is 1. Since 1 over 1 is equal to 1, then the value of our expression is 1 when x is 0. Now when x is increasing, this denominator will be increasing. If this denominator will be increasing, then the value of our expression will be decreasing. Then we have a graph that is decreasing as we increase the value of x. Now if x is infinity, then this denominator will be infinity because e raised to infinity is infinity. But 1 over infinity is 0, so we will have a graph that approaches 0 as x approaches infinity. If x is decreasing from 0 to negative infinity, the value of our expression should be same as if x is increasing from 0 to positive infinity. So we will have a graph similar to the one when x is positive. So this graph from negative infinity to positive infinity is e raised to negative x squared. Now the value of this integral should be the area below this graph. From here, we can divide this integral, into two parts, from negative infinity to 0 and from 0 to positive infinity. So let's do that. This is equal to integral of from negative infinity to 0 and from 0 to positive infinity. So this integral is from here to here, which corresponds to this area. And this integral corresponds to the area in here when x is positive. If you try to analyze carefully, their areas are equal. It means that the value of this integral and this integral are the same, so we can rewrite it as 2 times integral of e raised to negative x squared dx from 0 to infinity. Now let me get this integral. This integral corresponds to the area in here. So what we're gonna do is to evaluate this integral, then multiply by 2 to get our final integral. The value of this one can be constant, can be infinite, can be undefined. Now it is illogical to assume first that it is a constant, then prove later on that it is indeed a constant. So what we're going to do is to prove first that it is a constant. If it is a constant, then it should be less than infinity. So how can we prove that? Now in order to do that, let us divide this region into two pieces. One from 0 to 1 and one from 1 to infinity. So we will have the integral e raised to negative x squared dx from 0 to infinity will be equal to integral from 0 to 1 and from 1 to infinity. The value of this integral is this region. Since e raised to negative x squared is continuous, then this area is constant, or rather less than infinite. So we have here a value of the integral which is a constant. Now for this one, from 1 to infinity, the curve is asymptotic. We don't know if it is either a constant, an infinite, or undefined. So to evaluate this, let me get again this expression e raised to negative x squared. We can rewrite it as 1 over e raised to x squared. Or we can rewrite it again as 1 over e raised to x squared. And it is also equal to 1 over e raised to x times 1 over e raised to x. Now, our 1 over e raised to x, when x is 1 until infinity, from here, its value is, when x is 1, then it is 1 over e, and when x is infinity, it is equal to 0, because 1 over infinity is 0. But since 1 over e is less than 1, because e is 2.7 something, and it is greater than 1, then we can rewrite it as 1 over e raised to x from 0 to 1. Now, if that is so, then this is just a fraction. So we can say e raised to negative x squared is just a fraction of this one. That is, e raised to negative x squared is less than 1 over e raised to x, or e raised to negative x squared is less than e raised to negative x. Since e raised to negative x is greater than e raised to negative x squared, then its graph should be above e raised to negative x squared from 1 to infinity. So the area below that e raised to negative x from 1 to infinity should be higher than the area below the graph of e raised to negative x squared from 1 to infinity. So we have here integral of e raised to negative x squared dx is less than integral of e raised to negative x dx from 1 to infinity. Now, we can evaluate this integral. This integral e raised to negative x dx from 1 to infinity is equal to negative e raised to negative x from 1 to infinity. Or, when we substitute infinity for x, we'll get negative 1 over e raised to infinity, or negative 1 over infinity, or 0. So we'll get 0 minus, if we substitute 1 to x, we will have negative e raised to negative 1. So this one is minus, and negative will get positive e raised to negative 1, or 1 over e. So this one is 1 over e, and this one, which is this one, is less than 1 over e. Now, since this is a constant, we can designate it as b. For this one, we don't know yet if it is a constant, infinite, or undefined. Let us designate it as a. So a equal to integral of e raised to negative x squared dx from 0 to infinity. Since this one is less than 1 over e, so we'll have here less than b plus 1 over e. But since b and 1 over e are constants, then their sum should be constant also. Since it is a constant, then it is less than infinity. Therefore, a is less than infinity, or a is a constant. Thus, a is a constant. So now, when I put here x, it doesn't matter really what variable can I use. I can use y or I can use z, and whatever it is, it should have the same value of its integral. So this one should be the same with that. Now, we can multiply this equation by a, which is a constant. Then we'll get a squared is equal to, we can move out a inside the integral, so we'll get integral of a e raised to negative y squared dy from 0 to infinity. But a can be this one, so we'll get here integral of integral e raised to negative x squared dx, e raised to negative y squared from here dy. This is from 0 to infinity, and this one is 0 to infinity, so we'll have here 0 to infinity. We can rearrange this one, so we'll have here, now if we rearrange this one, we can combine both e, so we'll have double integral 0 to infinity, 0 to infinity, e raised to negative x squared plus negative y squared is negative x squared plus y squared. So we have here dx dy, which is equal to a squared. Now let us evaluate these integrals. In order to evaluate this, we can convert them into a polar coordinates. Let x is equal to r sine theta, y is equal to r cosine theta. These variables are actually related in a right triangle. This is x, this is y, the hypotenuse is r, and the angle is theta. So we can have a circle here. Assume that it is a circle and this is a center of the circle, and we have here the radius r. So we're changing the variables from x and y into r and theta. There are several approaches in this transformation. One of these is a geometric approach, which is the most popular, where we will substitute this one and this one in here and in here respectively, and equate dx dy equal to r dr d theta. So let me show you. We can have here a right triangle like that, x, y, r, theta. Then let us increase r with an infinitesimal amount and also theta with infinitesimal amount. This is dr and this is d theta. So the area here, we can determine that by multiplying dr with the length of this arc. This arc is a portion of a circumference, and that portion is d theta over 2 pi radians. So let us just multiply it by the circumference of the circle to get the arc length. So we'll have r d theta for our arc length. Then the area of this region is this one, times this one, which is r d theta times dr. Or we can rearrange this as r dr d theta. So in this Cartesian coordinate, the area here is dx dy. Here, this is r dr d theta. So we can transform this into a squared is equal to double integral. Then let us substitute this one and this one in here and here. So we'll have here x squared is r squared times sine squared theta plus y squared is r squared cosine squared theta. And we have here dx dy, which is equal to this one. So here, the value of x is from 0 to infinity and y also from 0 to infinity. So we can have here, if x equals 0, since x is from 0 to infinity, then we will have a horizontal line with length r equal to y. So we'll have here r will be equal to y, and the angle is, this is horizontal, so our angle is 0 radians. Now if x is infinite, so this one is infinitely long, so our figure will be just an infinite vertical line. So r will be infinity, and angle is, this is 90 degrees. So we have here pi over 2 radians. Now, if y equals to 0, then we will have here a vertical line with r equal to x. So r will be x, and the angle is, since it is vertical, then our angle is pi over 2. Now, if y is infinity, then we will have an infinitely long horizontal line. So r will be infinity, and angle is 0. So here, r can be from y or x until infinity, but x can be 0 and y can be 0. So r will be from 0 to infinity. Now here, the angle is from 0 to pi over 2. So we'll have here 0 to pi over 2. We will have no problem with that because, as you can see, our transformation functions are monotonic for r 0 to infinity and for theta 0 to pi over 2. Now, this one, this is equal to r squared times sine squared theta plus cosine squared theta, and this is 1. So we will have here r squared, then our a squared is double integral e raised to negative r squared r dr d theta from 0 to infinity, and here from 0 to pi over 2. There is another approach which is more rigorous. Let me show you how to do it. So from here again, let me show you the equation. So we can have an integral for r theta with variables r theta dr d theta equal to double integral f in terms of x and y for x and y dx dy, using a theorem that f r theta is equal to f for x and y we have here a inverse transformation function in terms of r theta, and we have another one because we are dealing with two variables, and we have here the absolute value of the Jacobian. Now for this one, we can have f for x and y, h1 r theta, h2 r theta. h1 is this one, h1, and the second one is h2. Now this one is equal to the original f for x and y, which is this one, e raised to negative x will be substituted for h1 and h2. So x, this will become r squared sine squared theta, like this, then plus y squared, which is r squared cosine squared theta, which from here, and we know that it is equal to e raised to negative r squared. So we can have here r squared sine squared theta plus r squared cosine squared theta, which is equal to e raised to negative r squared. Now for the Jacobian is the determinant of partial derivative of our first inverse transformation function, which is this one, with respect to one of its variable, and we have here h1 respect to theta, then partial derivative of h2 with respect to r, partial derivative of h2 with respect to theta. This is a determinant. So we will have here, let's multiply the diagonal with this one times the partial derivative of h2 with respect to theta minus this diagonal times partial derivative of h2 with respect to r. Let me rewrite here those transformation functions. X equals to r sine theta and y is equal to r cosine theta. Then partial derivative of h1, this is h1 and this is h2. Then partial derivative of h1 with respect to r is, so theta will be a constant but r is a variable, so we will have here sine theta. Partial derivative of h2 with respect to theta is, so theta will be a variable and r is a constant, so we'll have here r times negative sine theta. Then here, partial derivative of h1 with respect to theta is, so theta will be a variable and r is a constant, so we'll have r cosine theta. And partial derivative of h2 with respect to r is equal to, so in this case r is a variable and theta is a constant, so we will have here cosine theta. Then our Jacobian is, this one is sine theta times this one is this one, then minus this one is this one, and this one is this one. So we will have here, let us collect similar terms, negative r. Then we have here sine squared theta plus cosine squared theta, because we got already the negative r. So we'll have here negative r. Now for our this one f r theta is equal to this one, which is this one, e raised to negative r squared, and the absolute value of the Jacobian is this one. Removing the negative, we will have r, or r e raised to negative r squared. Now for this one we can now construct this, and this one is equal to that one, which is equal to a squared. So this one is equal to a squared. We will have now a squared is equal to double integral, and this one r e raised to negative r squared, and we have here dr d theta For our limits, we have already determined this in our geometric approach. Remember that this is 0 to infinity, and this one is from 0 to pi over 2. Now we have same equation, this one and this one, for different approaches. Now we are ready to evaluate these integrals. For the inner integral, let me rewrite it in here. Integral of r e raised to negative r squared dr from 0 to infinity, which is equal to, please take note that the derivative of e raised to negative r squared is equal to negative 2r e raised to negative r squared. Since we don't have negative 2 here, compared to this one, we need to multiply negative 1/2 for that one to make it equal to this one, so that its integral is this one. Now, we can now write here e raised to negative r squared as the integral of this one. Then this is to be evaluated from 0 to infinity. If we substitute infinity for r, we'll get e raised to negative infinity, or equal to 0, which is 0, then minus. When we substitute 0 for r, we'll get e raised to negative 0 or e raised to 0, but e raised to 0 is 1, so we'll get negative 1/2, which is equal to then negative and minus plus, so we'll have 1/2. Then for our a squared, we will have integral of, for the inner we'll have 1/2, and now d theta from 0 to pi over 2. And this one is 1/2 of theta from 0 to pi over 2. Then if we substitute pi over 2 in here, we'll get 1/2 times pi over 2. Then minus, substitute 0 to theta, we'll have 0, so we'll get pi over 4. Then our a is equal to square root of pi over 2. Now, this one is a, which is this one. Then what we need is 2 times a. So let me rewrite it in here. Integral of e raised to negative x squared dx from negative infinity to positive infinity is equal to 2a, is equal to 2 times square root of pi over 2 is equal to square root of pi. Now this is our desired value, which is the integral of e raised to negative x squared dx from negative infinity to positive infinity.